Hello everyone, welcome to this video. In this video, we'll be talking about rotations of a tetrahedron. So this is a 3D structure where this form has applications in where most of the molecules which are available in chemistry with us. For example, if you remember from your school studies, we were studying about this CH4, which was methane, right? So if you remember, while studying the geometry and shape of such molecules, with this one C, 4 hydrogen atoms, they were attached to each other, to this carbon, through the structure of tetrahedron. So that means when you join all the hydrogens together, so they would form a structure which would be tetrahedron. So tetrahedron, this is having 4 vertices, right? So let's call the 4 vertices, for the sake of convenience and identification, as this one as 1, this one as 2, this one as 3, and this one as 4. Right? So you see, this is a 3D structure where this is one face, right? This is another face, right? This is the third face, which is at the bottom, right? And this is the fourth face, which is present behind us, right? Behind the screen. So seeing this thing, what all rotations does this tetrahedron have, and how is it related to our group theory? So let's see this here. So you know what is the group A4? That is an alternating group, right, having 4 elements, having a degree 4. So in this, it would have 4 factorial by 2 elements within it, correct? Okay, and it consists of all the even permutations. So here the elements of A4, we are saying that describes the 12 rotations which are possessed by tetrahedron. So first of all, let's see what are those 12 rotations, how we may rotate a tetrahedron such that the result is different in each of the case. One thing. Another thing, how they represents A4, right? So this is the other thing. So basically we are looking for even permutations. So the cycle, the rotation here could be represented in terms of even permutation. So let's see how this thing is achieved. So you see in the first figure here, we are keeping our tetrahedron as such and performing any not doing anything to it. So that means we can list this as the identity permutation. Why? Because it has no effect on this tetrahedron. Correct. Moving forward onto the second figure here, what we are doing, we are taking these 2 edges CD and AB, right? On these 2 edges we are marking 2 points. First point is this, second point is this. So we are taking this as diagonals, and then what we are doing, we are rotating it like this, such that this 2 moves to this 1 and this 3 moves to this 4, right? And vice versa. This 4 moves to this 3 and 1 moves to this 2. So that means we could write this in permutation form as 1, 2 and 3, 4. So product of 2 transpositions. Next, what we are doing here in the third figure, if you can see, we are taking the this edge AC and the edge BD here, and taking 2 points here on this edges, and then rotating rotating about this straight line such that 2 maps to 4, this 2 goes to 4 and this 1 goes to 3. So this is difficult to view in 2D, but however you can have a insight of this thing. Okay, for the last figure, we are rotating it such that 1 goes to 4 here, 2 goes to 3. So it is like this. So this is about rotating it along 4 different axes. Now what about planes? We know we have 4 planes here. So accordingly we could rotate it plane wise. So one plane here forms a triangle. Each of the 4 planes form a triangle here, right? Having 3 edges. So we can rotate this triangle. Say this is 1, this is 2, this is 3. So we could have it like this, 2, 1 and 3, and we could also have it like this, right, where we have 3 and then 3 here, and then what, 1 here, 2 here, and things like that, right? We can rotate it like this or like this, whatever is suitable to us. So let's see, in rotating it clockwise or anti-clockwise gives us what. So suppose in the next figures that we have, we can see here on the screen, you can see I have shaded this particular plane, right? For this plane, you see 1, 2, 3, this form a triangle of which is a plane. So now we are just rotating this plane in the anti-clockwise direction. So you could see this 3 would go to 1, 1 would go to 2, and 2 would go to 3, and nothing would happen to 4. 4 would be on its place itself, right? So you can mark this permutation as 1 goes to 2, 2 goes to 3, and 3 goes to 1, right? Similarly, for this particular plane here that I have marked here, for this plane here, this 1 goes to 3, 3 goes to 4, and 4 goes to 1 when we rotate it anti-clockwise. Similarly, for this plane here, what we can do, we can again rotate it, and in this case we are rotating it clockwise. So here 2 is moving to 4, 4 is moving to 3, and 3 is moving to 2, right? So it is 2, 4, 3. So if you are looking at the anti-clockwise cases, so let's first discuss the anti-clockwise cases. So we have this case here, we have this case here. Moreover, for anti-clockwise, we have this case here where we can take this upper portion of this plane, which is behind the screen. Right here, when you rotate this triangle, this 2 would go to 4, 4 would go to 1, and 1 would go to 2. So this forms this particular cycle. And similarly, when we take this, not this one, when we take this particular plane here and rotate it anti-clockwise, so 3 goes to 4, 4 goes to 2, and 2 goes to 3, and this is what is our cycle. So these 4 figures here give us anti-clockwise movement of all the 4 faces of this tetrahedron. What about the clockwise movement? For the clockwise movement, you can see this figure here. We have this plane. So here 2 goes to 4, 4 goes to 3, and 3 goes to 2, and nothing happens to 1. So this is the permutation. And similarly, for this figure here, for this particular plane, we have 4 moves to 2, 2 moves to 1, and 1 moves to 4. So that means this gives us the permutation 1, 4, and 2. Similarly, we have the figure here for this particular plane here. When we rotate it clockwise, we would have 2 moving to 1, 1 moving to 3, and 3 moving to 2. So this gives us the permutation as 1, 3, 2. And for the last one, when we rotate this particular plane clockwise, so what we are doing, we are moving this 1 towards 4, 4 towards 3, 3 towards 1 again, and 2 is kept as constant, correct? So these 12 figures here represent 12 permutations, which I have listed down here within this brackets. So here this epsilon represents the identity permutation, and if you notice, all of them are even. You know already identity is an even permutation. These 3, they are the product of 2 transpositions, so therefore they are obviously even, and all of them, they are 3 cycles. And you know, you can represent 3 cycle as product of 2 cycles, correct? So every one of them could be represented in as a product of even number of transpositions. So therefore we have all permutations as even, so therefore they all form 12 as because the number of members which are present in A4, they would be 4 factorial divided by 2, which is 12. So you see here we have 12 members here in this case. So next, what we can do, we can create a Kelly table for this. This is I am leaving this as an exercise to you. What you can do, you can name all these 12 elements as alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 9, alpha 10, alpha 11, and alpha 12. And then you can list all of them here as row wise, and all of them here as column wise, correct? So after listing all the elements here, what you can do, you can multiply the permutation. So you can see what is alpha 1 multiplied with alpha 3. So basically you would have to perform this thing. Alpha 1 is your epsilon, which is the identity permutation, multiplied with your product of transposition. So you see identity does nothing to the permutation, so it is just alpha 3. So the answer here would be alpha 1 multiplied with alpha 3 is alpha 3 only, right? So in a similar manner you could calculate all these permutations. So after performing all such calculations, 12 into 12, 12 entries are here and 12 entries are there, so in total 12 into 12 calculations would be required in order to complete this table here. So after performing this, you would have this as the set of table. So you could match your entries with this table and see whether the same Calais table is obtained by you for this kind of alternating group or not. So I hope you understood this one, and I am pretty sure you can very easily perform this multiplication of two different permutations, which we have discussed in the previous videos very well, right? So well, that is it for this video. Thank you for watching.